July 2025. Astronomers spot Three-Eye Atlas, only the third interstellar object ever seen racing into our solar system. Its speed is impossible, but then everything changes. The James Webb Space Telescope detects a steady, pulsing glow coming from its core like no simple rock should ever emit. The object's brightness is triple what's expected, with no comet tail, no flicker. Its rotation is clockwork steady. Then comes the shock. Multiple teams confirm a thermal heartbeat, pulsing every few hours. This is followed by a cascade of strange radio signals that match no known natural process. If this is real, it could be the first evidence of something built, not born, heading right for us. So, what is Three-Eye Atlas? And why does its arrival have the world's top scientists demanding answers? It all began on August 6, 2025. Deep in the data stream from the James Webb Space Telescope, a group of operators flagged something that just didn't add up. The first infrared frames of Three-Eye Atlas showed a concentrated glow right at its core. It wasn't a scattered haze or a diffuse coma, just a tight, isolated source, bright enough to outshine the surrounding dust. The readings came in clean, with no sign of instrument error or solar flare contamination. On the raw plots, the heat signature stood out, a white-hot core fading into colored bands, all centered on a nucleus no telescope could actually resolve. The Webb team, led by senior instrument scientist Dr. Lena Marvich, checked their calibration logs, then ran the numbers again. The emission was steady, holding at levels 3 times higher than any model predicted for an object this size and distance. There was no tail, no flicker, just a fixed, unwavering beacon. The team's internal chat exploded with questions. Was this outgassing or something else entirely? They immediately started checking archives. Data from Hubble and TESS earlier in the summer hinted at an active object, already glowing far beyond Jupiter's orbit, long before sunlight could trigger normal cometary activity. But nothing in those old records matched the clarity or intensity of Webb's new images. For the operators, it was clear this wasn't a routine discovery. The heat was coming from deep inside, not from the sunlit surface. And whatever was powering it, the usual rules did not apply. Meanwhile, the optical survey teams, led by the Atlas Group in Chile and analysts at Hubble, began their own round of checks. Their first concern was the brightness. By every standard metric, Three-Eye Atlas shone at nearly 3 times the intensity expected for a body of its estimated size and distance. Light curve studies, plotted over weeks, showed a steady, unwavering output. No dips, no surges, no evidence of the flickering usually caused by jets of gas or uneven surfaces. For comparison, typical comets brighten and fade as they tumble, their icy crust venting in fits and starts. Here, the pattern was almost flat, with a measured rotation period of about 6 hours, plenty of time to reveal any major surface activity, but nothing appeared. Hubble's high-resolution images searched for the classic tail, that streaming plume signaling a comet's ice turning to vapor. Instead, the object was wrapped in a tight, teardrop-shaped cocoon, more like a shroud than a tail. Analysts noted that even at 6 astronomical units from the sun, where sunlight is weak and most comets are dormant, Three-Eye Atlas was already active, glowing against the black. No model of solar heating or standard outgassing could explain the intensity or the timing. These contradictions left the optical teams with a puzzle, a body too bright, too steady, and too self-contained to fit any familiar category. The usual comet rules just didn't apply. For the researchers, the next step was clear. If the light wasn't coming from the surface, maybe the answer lay deeper inside. Infrared analysts on the Webb team began dissecting the time series data, looking for any sign of a pattern in the heat pouring from Three-Eye Atlas's core. What caught their attention wasn't just the intensity, but its rhythm. Every 4 hours, the central glow swelled and faded in a slow, deliberate cycle. The pulse was unmistakable steady, almost mechanical, with energy peaking at the heart and radiating outward in waves. There was no random flicker, no chaotic outburst. The data logs filled with timestamps, each one marking a rise and fall that repeated with uncanny precision. Dr. Marovich and her group mapped the intervals against the object's rotation and orbital parameters, searching for a natural cause. Nothing lined up. The heat didn't track surface features or solar input. It pulsed from deep inside, untouched by the changing angle of sunlight or its distance from the sun. To the Webb operators, it looked less like a comet's outgassing and more like the heartbeat of something engineered. Radio observatories from California to South Africa tuned their arrays to 3I Atlas, searching for any trace of electromagnetic activity beyond the optical and infrared. The Allen Telescope Array, led by Dr. Kavita Ralph, began sifting through hours of wideband data, filtering out background hiss and satellite spillover. Then, the team isolated something that didn't belong, a faint, narrow band pulse repeating every 4 hours, unwavering in its rhythm. A Fourier analysis confirmed the pattern, a stable carrier wave cutting sharply against the static, with a repetition too precise for random cosmic noise. Over several nights, the pulse held steady, yet its timing drifted in lockstep with changes in the solar wind, matching fluctuations tracked by space weather monitors. Independent teams at Meerkat and Effelsberg verified the signal, ruling out local interference and terrestrial sources. The pulse's persistence, its subtle environmental shifts, and its cross-hemisphere replication forced a new question into the open. Was this a natural process, or a deliberate transmission from something aware of its surroundings? In mid-August 2025, the anomaly deepened. Webb's live feed caught a sudden flare. 3I Atlas brightened by nearly 40% in less than an hour. The test satellite, still tracking from Earth orbit, confirmed the spike. Every telescope trained on the object registered the same surge, not just in visible light, but in thermal output. For a brief window, the object radiated as if something inside had just powered up. Then, just as quickly, the numbers stabilized, but at a new elevated baseline. Attention shifted to the orbit. Marco Micheli and the ESA's Near-Earth Object team ran updated models. The predicted path, calculated from months of data, no longer matched reality. Instead of drifting passively, 3I Atlas had veered, its trajectory bending closer to the plane of the solar system. Micheli's group debated the cause. Outgassing? Measurement error? Or something less familiar? The acceleration just didn't fit any known comet behavior. For the first time, the data hinted at a maneuver, with the flare and the course change locked together in the logs. The question now pressed harder. What kind of object changes course mid-flight, and why here at the edge of the ecliptic? On August 18th, Webb's instruments handed the baton to the spectroscopists. Carrie Lissa's group at Johns Hopkins took the lead, poring over the raw spectra from 3I Atlas. The usual comet markers, water, ice, carbon dioxide were present, but layered on top of them sat a puzzle. Several absorption lines refused to match any known catalog. The reflectivity profile hinted at metallic alloys, some echoing rare earth elements found only in advanced manufacturing here on Earth. Buried in the data, a handful of features aligned with theoretical quantum material structures, described in physics papers but never observed in nature. For the team, the evidence pointed away from random cosmic chemistry and towards something that looked, at least on paper, engineered. By late August, access to raw telescope feeds began to tighten. Internal memos from NASA and the ESA referenced new data protocols, citing planetary security. The SETI working group, led by an anonymous coordinator, debated whether to transmit a mathematical signal toward 3I Atlas. After a tense vote, the message was sent. Prime numbers, the periodic table, basic constants. 72 hours later, a narrow band reply arrived, timed to the second. The return pulse was distorted, but its pattern matched the original transmission window. Agency officials immediately locked down the data, rerouting communications to classified channels. Outside, speculation surged. Inside, the atmosphere shifted from curiosity to something closer to caution. At the August IAU debate, 4 leading models outgassing jets, radiogenic heating, dust scattering, and mass estimate errors were tested and found lacking. None could explain the full chain of anomalies. Now, With the September flyby approaching, the countdown is on. Every instrument will be watching, hoping for the data that finally settles the question. Let's recap the facts. On August 6, 2025, the James Webb Space Telescope recorded 3I Atlas emitting infrared light 3 times brighter than predicted. Over the following weeks, teams documented a pulsed heat signature, a repeating radio signal, and a sudden 40% flare that coincided with a shift in its trajectory. Facts confirmed by TESS, Hubble, and ESA orbital data. Spectroscopic analysis revealed rare earth alloys and absorption lines unknown in any catalog. Despite multiple independent reviews, natural explanations were all ruled out by the International Astronomical Union. As of late September 2025, its closest approach is imminent. 3I Atlas challenges every current model of interstellar objects, and its passage past Earth will be a decisive moment for planetary science. Thanks for watching. If you found this journey into the unknown as fascinating as I did, make sure to hit that like button and subscribe for more deep dives into the mysteries of our universe. See you next time.